Hello! Welcome to Sequences and Series Unit 7. Alright, so my favorite sequence we're going to talk about right off the bat is this guy right here. I don't know if you've ever seen it before. Whoops. You might recognize it. It is called the Fibonacci sequence. So, Fibonacci sequence is beautiful sequence. It's my favorite. It's in art all over the place. More so the ratio, which I'm going to talk about in a second. It's called the golden ratio. But first, let's talk about Fibonacci sequence. So the Fibonacci sequence is the previous two numbers added together give you the next number. So if I took 0 and 1, that gives me 1. If I took 1 and 1, that gives me 2. Oh, that looks like a very sad man. So if I seem a little down at this point, I just videotaped this right before this. It took me 30 minutes and it didn't have sound on. Anyway, so here we go. So Fibonacci sequence, what's cool about it is if you divide, say for example, 4 into 7, it'll give you closer and closer number as, say, for example, 7 to 11, and 11 into 18, and 18 into 29, so on, so on, so on. It'll give you closer and closer and closer to this number, which is called phi. We call it the golden ratio when we divide the previous number by the next. And this number is in all of nature. It's also in paintings by like Leonardo da Vinci. And if you've ever seen like maybe memes or conversations about like ultra beauty, they will say that a perfect face has the symmetry of the golden ratio all over the place. Your hands have it, your arms have it, it's all over. It's a cool topic to Google, by the way. So anyways, a sequence. Let's get definition going here. A sequence is a set of numbers with a particular order or pattern. Each number is called a term. Important to know. And is that true for the Fibonacci sequence? Does it have a particular order or pattern? It does. The pattern comes from the two previous numbers being added together. So we have two types of sequences we're going to talk about. First is finite. And its definition is going to be a sequence with a, you guessed it, finite number of terms. Okay, an example of a finite sequence. I'm going to get creative here and go 1, 2, 3, I don't know what comes next, 4, 5, there we go. And how many terms do we have in this finite sequence? Remembering each number is going to be called a term. We have 5 terms. Well done. All right, next, I should switch colors before. Oh well. We'll go orange, orange, green, green. A infinite sequence is a sequence, you guessed it, with an infinite number of terms. An example of this would be something like whole numbers, 0, 1, 2, 3, 4, and so on. And how many terms do we have? Infinite. Oh, that's supposed to be a brace. That's a terrible brace. Okay, so term notation. The first term is denoted a sub 1. And each subsequent term is denoted a sub n plus 1, where n plus 1 is the term number of the sequence in the sequence. So for example, in this infinite sequence, identify the following terms. A sub 1, 2, a sub 5, 14, a sub 8. Oh boy. Sorry if I get distracted. I'm still paranoid that this isn't recording the sound. Hold on. All right, I think it's good. All right. So a sub 8. Here we go. 1, 2, 3, 4, 5. Oh boy. Keep going. So we have to figure out the pattern before we can go on though. So I can see it is going up by 3 each time. So that's easy. So it's going to be 17, 20, 23, 26, 29, 32, 35. Let's keep going till 44. So term 8, we know 5 is 14, so 6, 7, 8, 23. We know we know 8 is 23, so 9, 10, 11, 12, 13, 14, 41. So a sub 14 is 41. There we go. Let's go red now. All right, so since each term value is paired with exactly one term number, a sequence is a function with the following properties. N is going to be our domain. A sub n is going to be our range. And the domain is called, the domain is a set of term values like we talked about. A sub n is going to be called term numbers. Term values, term numbers. And in an infinite set, the domain of the set is of natural numbers. Natural numbers. So here we go. We'll talk about the natural numbers later. So when we are talking formulas for our sequences, we have two different ways of doing it for now. We have our recursive formula and we have our explicit formulas. First, let's talk recursive. A recursive is a rule in which one or more previous terms are used to generate the next term. So remember the Fibonacci sequence: 0, 1, 1, 2, 3, so on, so on, so on. What it's saying is the previous terms are used to generate the next term. That was true. We needed 0 and 1 to get 1. We needed 1 and 1 to get 2. We needed 1, 2 to get 3. That's important. They use Fibonacci sequence as well. I don't blame them. It's a beautiful sequence. Oh, I keep writing 4. I get like 1, 2, 3. I get excited. I can't control it. 5, 8, 13, 21, so on. So in the sequence, a sub 1 is 0, a sub 2 is 1. Then for each subsequent term, so we have to go general here. So a sub n, we have a sub n equals. And let's just use an example here. Let's not say n, let's say a sub 6. We know a sub 6 is equal to the two previous terms. So what is a sub 6? 3, 4, 5, 6. A sub 6 is equal to 5, because that's the sixth term. And we know it's equal to the two previous terms. So how would we write that? That would be a sub 5 plus a sub 4. Because a sub 5 is 1, 2, 3, 4, 5, 2. A sub 4 is 1, 2, 3, wrong one. A sub 5 is 3, and a sub 4 is 2. So just put them the other way. Doesn't matter. You can do it either way. So that is going to equal a n minus 1 plus a n minus 2. So it's saying if we had a sub 6, for example, we subtract 1. That gives us a sub 5 plus n minus 2, a of 6 minus 2, which is a sub 4. So let's check our answer. 1, 2, 3, 4, 5, 6. A sub 5. 1, 2, 3, 4, 5. A sub 4. 1, 2, 3, 4, 2. Yep. Check. It works. Wow, that's great. All right, so that gives us a tool to be able to do these. What if they give us the rule and we just got to solve it? So that's what it's asking. What if it gives us the first one, 25, and we got to find the first 5 terms? So we have one of them. We got to find 4 more. So a of n is a n minus 1 minus 7. What that's saying is if we have a of 1, we get the previous term minus 7. But it's telling us n has to be greater than or equal to 2. So we don't come to not being able to find it. So if a is a sub 2, we get a sub 2 minus 1, which is a of 1 minus 7. Oops. We know a sub 1 is 25. So 25 minus 7 is 18. And we keep doing that. So if we had a3, that's a 3 minus 1. 3 minus 1, which is a sub 2. a sub 2 minus 7. Do we know a sub 2? We do know. It's 18. So 18 minus 7 is 11. And so on. We don't even need to do this. We see the pattern. We get 4, negative 3. And there's our 5 terms. Nice. Okay. Number 2 looks pretty similar, so I don't think we need to do that. So is 3. Yeah, we'll do 3 as well. So a of 1, we already got it. 40. Let's change colors, actually, to dark blue again. 40. All right, a sub 2. A sub 2 equals 1/2 of a 2 minus 1. So a sub 1 plus a sub 1. We already know a sub 1. A sub 1 is 40. So half of 40 is 20. 20 plus 40, 60. Let's try the next one, a sub 3. That's 1/2 of a of 3 minus 1, which is 2, a sub 2. So that's the same. We know a sub 2, that's 60. That's 60. So 30 plus 60 is 90. All right, let's keep going. I'm going to make you smaller, sir. Move up there. All right, so a sub 4 is 1/2 a sub 3 plus a sub 3, which is 1/2. 90 plus 90. 45 plus 90 is 135. There we go. So, last one. I'm going to skip it and just write the answer. 2 under 2.5, but that's how you do it. Number 4, very similar. We have a sub 1. Change colors again so we don't get confused. 8. And then we have the second term as well. Nice. We only need 3 now. And we are doing when n is greater than or equal to 3. Good. So now we're looking for a sub 3. And that's going to equal to a sub 2 over a sub 1. And we know a sub 2 is 10. And we know a sub 1 is 8. Oh, that's why we need 2 terms. So now we have 5/4. Next, a sub 4. That's going to be a sub 3 over a sub 2. That's going to be 5/4 divided by 10, or times 1/10. And that's going to be, I already put a little comma there. Whoops. 5/40, which is 1/8 when I divide by 5. So a sub 5 is going to be a sub 4 over a sub 3, which is equal to 1/8 divided by 5/4, or times 4/5. That's going to be 4/40, which is 1/10. And we are done. This isn't too bad. Let's go different colors. I'm going gray. The never appreciated gray. All right, so let's write a recursive formula. This is where it gets a little bit trickier, but it's not too bad. Here we go. Oops. Let's see here. All right, so recursive formula. We kind of just follow their pattern. That's all we got to do. So we have our first term. We know our first term, which is what? A sub 1 equals 9. Okay, semicolon. Now we're looking for our general formula. All right, this is actually kind of easy one. Going up by 4. That's nice. So we know it's going to be whatever the previous term is plus 4. Right? So say, for example, we had a sub 3, which we know is 17. It would be the previous term, a sub 2, plus 4. And we know a sub 2 is 13. So there we go. But we got to write our n being greater than or equal to 2. We can't have it being done with our first term because we don't have a previous term before that. You need the previous terms to be able to determine the next. That's the point. All right. Oh, boy. Number 6. All right. So you add 2. You add 5. You add what? All right. So that's not going to work. So we have to think of another pattern. This is fun. You get to try and figure out the patterns. So let's see here. All right. Okay. What if I did 1 plus 3? So times 2. Would that give me 8? It would. So let's see if it works with 3 plus 8 times 2. Does that give me 22? It does. That's it. So it's the two previous terms add together doubled. So for example, oh man, eraser, 1 plus 3 times 2. That gives me 8. And it also is 3 plus 8 times 2. That gives me 22. And also 8 plus 22 times 2. That gives me 60. Nice. That's it. All right, so a sub n is going to be equal 2 times 2 previous terms. So similar to this Fibonacci sequence we wrote before, it's going to be a sub n minus 1 plus a sub n minus 2. That's going to be the second, the two previous and previous, where n has to be greater than or equal to, since we need the first two terms, it has to be greater than or equal to 2, but yeah, it works. So there's the recursive formula style. So now let's go to explicit. Explicit is similar to a function, if not the same times. So it's going to be a lot more familiar and hopefully easy for you guys. So explicit formula is a rule. Yeah, let's keep gray. A rule in which the nth term is defined as a function of n. Yeah, sounds like a function. Oh. So for example, give the first terms of the sequence. All right, easy. If it was 1, if n equals 1, that's going to be 6. If n equals 2, that's going to be 11, and so on. 3, 16, 4, 21, 5, 26, piece of cake. What about this guy right here? Let's change colors. I'm tired of gray. Let's go brown, another unappreciated color. So if we had n equals 1, that would be a sub 1 equals 3 halves to the 1 minus 1, which is 0. That gives me 1. And then to the, when n is 2, that's going to be 3 halves to the first power, 3 halves. And then 3 halves to the second power, 9 fourths. Third power, 27 eighths. Fourth power, 81 16th? Yep, 16th. Check. All right, they're all similar. Let's do number 12. All right, so a sub n equals n. Oh no, it's not telling me to yell. This is a mathematical symbol. What does the exclamation point mean in math? Okay, it means factorial. Factorial. It's mostly used in probability, but, so say for example I had 4 factorial. That equals 4 times 3 times 2 times 1. All right. So here we go. So say I had the first term, a sub 1. A sub 1 equals 1 times, nope, that's it, minus 4, which is negative 3. A sub 2 equals 2 times 1 minus 4. That's the n factorial, or 2 factorial. So we get 2 minus 4, negative 2. Oops, why did I close it? Come on, Mr. Dustin. And a sub 3 equals 3 times 2 times 1 minus 4, which is 2. A sub 4 ends up getting you, let's see, I don't feel like doing it all out. So 20. And then 116. Close set, and we are done. So writing the rule for each sequence is a little bit trickier. So we need to find a sub 25 after that as well. So we know it is going up by 3, and then 5, and then 7, and then, ooh, what's going on here? So how do we find that? That doesn't help us. See if we can know any other patterns. Oh, these are all perfect squares. And each term in the sequence, when it's squared, gives you that number. Oh, that's it. So say, for example, it's a sub 1. When it's going to be 1 squared. A sub 2, 2 squared. A sub 3, 3 squared. A sub 4, 4 squared. Oh, that's it. So it's going to be a sub n, whatever that term is, squared. And yeah, so now we need to find a sub 25. And we already know that to be 625. There we go. Check, check. Not bad. All right, now let's do this one. Plus 2. Okay, yeah, this is the easy one. Plus 2, plus 2, plus 2. But how do we write it? Okay, so we need our first term. So let's say our first term is 9, and then it's going to be whatever the first term is plus 2? No. It's going to be the first term plus whatever the difference is times the previous term. So say, for example, we had 9. So if a sub 4, that's going to be equal to 15. That's going to be equal to 9 plus 2, the difference, times 3. Whatever the previous term is. So not term is, term number is. So that's going to be 9 plus 6, which is 15. There we go. All right, so what I would do, though, is simplify this after that. I would say a sub n equals 9 plus 2n minus 2, which equals 2n minus 7. So we then could say a of n equals 2n minus 7. So this sequence, this little formula we have here, will work quite often, almost every time. So we can remember that and use it in the future. All right, so we also need to find a sub 25. So what's a sub 25? That's going to be 25 times 2, which is 50, minus 7. Oh, that's not minus 7. Sorry, that's plus 7. So 50 plus 7, 57. There we go, and there we go. Okay, so last two. Write an explicit and recursive formula for each, or rule for each sequence. All right, let's do explicit first since we just did it. All right, add 3. Easy, easy. So we take our first term, and then we have our differences between each terms, and then we have whatever our subscript is, minus 1. There we go. So it's going to be, say, for example, we had a sub 6. Nope, 5. That was 16. So we have our first term times 3 times how many terms we went past the first term. So that is going to be how many terms from 4? 1, 2, 3, 4. Yeah, so similar to a multiplication. That's really what multiplication is anyway. So a sub 5 equals 16, and that's true. So our explicit formula, we can simplify this to 4 plus 3n minus 3, and then combine like terms. We get a sub n equals 3n plus 1. Check. All right, I'm going to erase that. Doink, 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 doink. I'm getting tired. All right, so let's do the recursive. Recursive says we need our first term to be 4, semicolon. And then a sub n is going to be equal to whatever the previous term was, plus the difference. And the difference is 3. All right, since we can't use 1, we have to say n is greater than or equal to 2. There we go. Same thing for number 16. What are we going up by? We're going up by 1/2. Going up by 1/2 each time. So we know a sub n is going to be equal to the first term plus whatever we're going up by times how many terms after we're looking for. So say this was a sub 4. So 1, 2, 3, 4. We are going 3 terms past the first, so that's going to be 3, or 4 minus 1. All right, and that, oops, I shouldn't write that. I should write that here. It's more specific. This is in general. So if I change that to 4, and I went n, it would be 1/2 plus 1/2 n minus 1. So this would give me, as it does, 2, and that was correct. So we can simplify this. A sub n equals 1/2 plus 1/2 n minus 1/2. The 1/2s cancel out. So we get a sub n equals 1/2 n. Check. Recursive is going to be, we have our first term. That's 1/2. And then our formula is going to be the previous term plus 1/2. That's easy. That's an A, not an N. 9, I mean. Okay. That's it. See you.